Okay. So for now, I'm going to share my screen. And let's continue the lecture where we stopped yesterday. So yesterday we introduced the way to calculate the distance, the horizontal distance based on the slope taping, and we can use the distance of the slope and the vertical angle or zenith angle to calculate the horizontal distance and also the vertical distance. There will be two examples that we just learned to use this method. And we introduced the first one by giving the length of the slope and the vertical angle. You can calculate the horizontal distance. The second one, if you are provided with the horizontal distance and the vertical angle, you can calculate the slope distance. Also, we have another one, a little bit complicated. Say that if the slope is measured as 250.542 meters, and we know the zenith angle is 84 degree 45 minutes and 30 seconds. What's the horizontal distance? So to solve this one, well, I will still encourage you to draw the figure about the problem, and then you will have a better understanding about what kind of problem you are trying to solve for this question. So we have the slope, and the sloping distance S is 250.542 meters, and we also have the zenith angle. Here you need to remember that the problem provides us with the zenith angle, so we have to find out the way to identify the zenith angle. So this is the zenith angle about the slope. And now the problem wants us to find out what's the value of the horizontal distance. Okay. If we go back to check the formulas that we provided about the relationship between the horizontal distance and the zenith angle, you can get that h equal to the slope distance times sine zenith angle. So this is different. If you are provided with vertical angle, this should be cosine. And we have the slope distance as 250.542 meters times the sinusoidal function of zenith angle is 84 degree 45 minutes and 30 seconds. Again, we need to convert this angle to the radian value. So the theta here, now theta z here would be 84 degree, and we need to convert all the minutes and seconds to the to degrees. So we have the minutes part as 45 minutes divided by 60 minutes, and for the second part, we have 30 seconds, and actually 1 degree is 60 minutes and 1 minute is 60 seconds. So it indicates that 1 degree is 3,600 minutes. So with that, you can find out the value of the zenith angle. I don't have the exact value. Let me just have a quick calculation about it. So the value is 84 plus 45 divided by 60 plus 30 divided by. So the angle in radian would be 84.75 83 degree, and then you can convert this one to radian. With that, that will be 250.542 times sine 84.7583 times pi divided by 180 degree. So that's the way for you to find out the radian. And with that, you can use the calculator or Excel to find out the value of the horizontal distance, which would be 249.494 meters. So that's the value of the horizontal distance based on the slope distance and the zenith angle. So this is the one way for you to use the slope taping for the distance measurement. And there's another way. It's like sometimes you are able to find out the actually in the survey it will be easy for us to measure the slope distance, and also we can use the transit level to measure the difference in elevation, which means that we can find out the vertical distance. That would be the, say, the letter H. With that, we can use the Pythagorean theorem to calculate the horizontal distance. So, for example, in this case, we are given the slope distance, and we are also provided with the vertical distance, say the letter H, and then we want to find out the horizontal distance. At this moment, we don't know the vertical distance or the zenith angle. Both of them are unknown. So in order to find out the horizontal distance, we have to recall the Pythagorean theorem. So with that, we have h squared plus letter h squared, which is the vertical distance, equal to s squared. So this is the Pythagorean theorem. So with that, we have the horizontal distance. It's very simple. The s squared, the slope distance, minus the h squared, the vertical distance. So that's the way for you to find out the horizontal distance. Also, if we are provided with h, but you don't know h prime, you can still apply the same equation to find out the vertical distance. So that is letter h equal to s squared, the square root of the s squared minus capital H squared. So that's the calculation from the slope and the horizontal distance to the vertical distance. And the next, we're gonna show you one example about how to use this Pythagorean algorithm to calculate the horizontal distance. So the problem is very simple. We have the distance of 130.508 meters. This is the slope distance, and we know the elevation between the two ends. That is 5 meters, and then we want to find out the horizontal distance. So still, you have to draw the a graph to show that problem. We have s equal to 130.508. We have h equal to 5.5 meters, and we want to find out the capital H, the horizontal distance. So with that, we can call the equation we defined in the previous page. So the horizontal distance equals to the square root of s squared minus letter h squared. So the calculation would be simple. 130.508 square minus 5.5 square, which will give you the horizontal distance as 130.390 meters. So that's the way for you to find out the horizontal distance based on the distances of the slope and the elevation difference. So with that, we are finishing the introduction about the taping, the fundamental method for you to conduct the taping measurement. Do you have any questions so far? Okay, if we don't have any questions, I will move to the next topic. Which will be the way for us to handle the errors in the distance measurement. So I'm gonna exit these slides. Okay. Okay. So following the fundamental distance measurement with tape, in reality, you will see a lot of errors in your measurement, and some of them would be the natures, the impact from the nature. Some may comes from the human errors, and as in the severe, we need to know how to solve the potential issues and how to correct the error. Okay, that's weird. It might be someone's trying. Okay. Someone might try to join this one. So anyone who is trying to join this one, could you just mute yourself? Yeah. Okay, that's pretty weird. It's the first time for me to see that. I hope the problem is solved. It looks like the problem is solved. Okay, I'll just continue my continue these slides. So basically, we can see three types of the errors in the distance measurement with tape. The first error is called the instrumental error, which would be the error from the table itself. It might be some errors from the scale, or it might be the errors from the from some of the it's a physical the property of the of its physical materials. The most common instrumental error is like the table is not of the standard length. For example, if the table said that in the market you can see the length of 1 meter, but in reality, if we compare with the standard tape, you will see that the 1 meter measured by the tape they are using may not be exactly 1 meter, might be 1 centimeter long or 1 centimeter short. So this is the error from the instrument itself. And once we know this error, there's always a way for us to do the correction. And the second type of the error is called the nature errors. It was caused by the surrounding environment when you are conducting the taping measurement. The most common environment impact will be the temperature, the tension applied to the tape, and also the sag effect. And this will actually be the three major errors we will need to correct for the for taping. And the last one would be the personal error. So that could be the it's not the issue of the tape, and it's just the wrong operations of the surveyors. For example, the tape might not be aligned to the line very well, and it's not quite horizontal. With that, you will have the wrong measurement about the distance. And also, if you don't, if the tape is not straight, then the reading from the tape will be very long. So usually for the personal error, you need to conduct the measurement multiple times with different surveyors. And by checking or comparing the result from different surveyors, you can easily identify the personal error. And there's a way for you to eliminate some eliminate some personal errors. So the once we know these errors, the most important part is like how we're going to correct the error in the measurement. Usually for the instrumental and nature error, they can be corrected mathematically, which means that we can find out the true value if we know the features of those errors. And this kind of correction is related to the natural properties, such as the temperature, tension, or the weight of the tape. And they could also be related to the if it's the error of the instrument itself, we need to do the calibration about the tape and then find out what's the errors in your tape. And once you finish your measurement, you can do the correction based on that. For the personal error, usually we can only correct them by repeating the measurement, by following the right steps to operate the machine or to use the tape multiple times, and you can try to remove the personal error. And also you can use some assistant tools, like you can try to use some benchmarks with the known distance to do the correction, and then verify your steps to remove the personal errors in your experiment. In these slides, we will actually focus on the correction from the instrumental error and the nature error. The first one we're going to introduce is about the variation in temperature. And we know that when the temperature increase, usually for most of the materials, they're going to expand a little bit. This also applies to tape. And for the steel tape, the expansion might be small, but for the PVC tape or the fabric tape, it might have a larger expansion. And also, if the temperature falls, the tape will contract a little bit, and those type of the effect will cause the error about about your reading. So so now we will have some questions like what happens for your readings if the temperature is high? Like, will the reading be smaller or larger? Do you have any ideas about that? The reading, I saw the answer, one answer about larger, but the answer is actually smaller. This might a little bit counterintuitive. So for example, if we consider a distance of 1 meter, and this is the true distance that you are trying to measure. You apply the tape. It has some scales on the top, and without if we don't consider the impact of the if there's no impact of the temperature, then you should read 1 meter from the tape, right? But if the temperature increase, your tape will expand a little bit. So with that, you will observe that your tape will expand a little bit. So now your 1 meter reading is not here. Instead, your 1 meter reading at the expanded location. So what you will observe is something smaller, maybe around 0.99 meters. So you will see that you will have smaller reading when the temperature increase. So in that sense, for the correction, you need to add this error from the this expansion from the temperature. And similarly, if the temperature is reduced, what you will observe, like you will have you will actually read a larger value. It might not be 1 meter, it might be 1.01 meter. So the 1 meter mark might be on the left. So with that, you need to subtract the smaller error from the temperature. So that's the reason. That's the exact reason you need to bring the pocket thermometer with you to do the experiment, and usually you need to record what's the temperature on that day, and you can find out the standard temperature, which is the temperature that the tape is calibrated. So at that temperature, you will not observe any errors from the temperature. Generally, for most of the tape, the standard temperature is 20 degrees. So at that temperature, there isn't any error, but this varies depending on different manufacturers. Basically, in order for us to do the correction of the temperature, we can rely on this equation. So the correction of the temperature is alpha times L times T minus T0. In this equation, alpha is the coefficient of the thermal expansion. So this is for one tape with one kind of the material, then the value of alpha is constant. And in this equation, the capital L is the measured length, which is the length you read from the tape. This is the actual reading. And T, capital T, is the temperature of the day that you conduct the measurement. The T0 is the standard temperature, which is the temperature that the tape is calibrated. And with this equation, if you see that if you do the experiment at T equal to T0, then you will always have CT equal to 0, means that the correction is 0. But if you have the if T is higher than T0, you will observe the correction is also larger than 0. And this means that you need to add the correction to the observed value. Like for this case, what you observe, L is 0.99 meters, and the CT based on calculation is 0.01. Then you add them together, L plus CT, that will be 1 meter. That's the true distance you measured. And similarly, if T is less than T0, you will have CT less than 0. Well, this is applied to the case in the second example. So you have L equal, you read from the table, L is 1.01, and CT is calculated minus 0.01. So you have the true distance is L plus CT equal to 1 meter. So that's the way for us to apply the correction for the temperature. So that's the first one. And the second factor is the tension. And I hope you all have already recorded the tension that you applied when you conduct the experiment this week. The impact of the tension is quite similar to the temperature. Basically, if we apply a very large tension, you will actually have stretch the tape and make it longer. And if the tension is smaller than the standard tension, then the tape will be shrunk a little bit and it's shorter. So there will be the similar effect. Say that the same we are considering the same distance that we're going to measure, the true distance of 1 meter. And now there's the question. So if we have the very large tension applied to the tape, what's the observation? What's the reading from the tape? Is it larger or is it smaller? Any ideas about it? Well, the yes, the answer is smaller. So it's still like the like what we will see for the temperature. If it's under the standard tension, then you have 1 meter reading. But with the very large tension, you will try to make it longer, and the 1 meter mark will shift to the right point. And what you're gonna read might be something 0.99 or 0.98, something like that. And if the tension is very small, then you will have different. You will need to you actually have a larger reading, and this could be something like a 1.02 or some other values. So that's the impact of the tension, and also we have the function to calculate the correction from tension. So the equation here shows the calculation about the correction of the tension. So basically, the correction of tension Cp equal to P minus P0 times L divided by A times E. Remember here, A is the cross-sectional area. It's different from the coefficient of the thermal expansion. But that is alpha. They look quite similar, but it's different. And the capital E is the elastic modulus of the steel or the other materials of the tape. And the L is the measured length, which is the reading from the experiment. And the P is the applied tension, that is the tension you measured when you conduct the experiment. And P0 is the standard tension, which is the tension you applied to calibrate the tape. So with that, we can conduct the we can estimate the value of the tension correction. And basically, if P is higher than P0, we have Cp larger than 0. That means that you need to add the correction to the observed value. And if P is smaller than P0, then Cp is also smaller than 0. And it means that you need to subtract the estimated value of absolute estimated value from the observed value. So that's the tension. And now let's see one example to check how we can use the this equation to do the calibration, to estimate the true distance measured by the tape. So assume that we have the light 100 feet tape. It's a standard with the full support under tension of 10 pounds, and the elastic modulus is 30 million pounds per square inch, and the cross-sectional area is 0.003 inches a square inch. And we want to find out the elongation for the increase in tens from 10 to 30 pounds. And this one wants us to find out what's the correction of the tension if you increase the tension from 10 to 30 pounds. So for this problem, I will go through the solution of this one, and I'll give you some chance to practice on the other examples by yourself. For this problem, you have all the assumptions about the length. The actual length of the tape is 100 feet, and the standard tension P0 is 10 pounds. We also have the modulus of elasticity is 30 million pounds per square inch, and the cross-section area is 0.03 square inch. And we want to find out the correction of tension. So with that, we can just recall the formula that we defined for the tension correction. Cp equal to P minus P0 times L divided by A times E. So we have P, the applied tension is 30 pounds. So you have the applied tension as 30 pounds. So with that, we have 30 minus the standard tension is 10 times the length is 100 divided by the cross-section area, 0.03 times 0.003. We have the cross-section area as 0.003 and the modulus of elasticity 30 million. So with that, we have the correction of the tension as 0.022 feet. So that's the correction for the 100 feet measurement. And if it's shorter, then you have to reduce to the proportionally. So that's the tension. And the next thing we have to consider is the impact of the gravity. So this impact is called the sag. So this is quite common when you place your tape on the uneven road, especially when you are working on the break tape method to measure the horizontal distance. So for example, when you put the tape between 2 points and they are all above the ground, or at least one side is above the ground for you to get the horizontal distance, then the actual curve is not necessary to be the a straight line. Instead, it will be a form of the catenary. So what you will observe is like from one end, point A, to point B, it's really hard for you to stretch the tape as in a straight line from A to B. And in reality, due to the effect of the gravity, it will form the curve. And that's an actual tape you will place for these two ends. And in this sense, say that if from A to B, the true distance is 1 meter, what do you think the distance you were measured? What's the actual reading? Is it larger or it is smaller? So any ideas? So definitely, yeah. So this time it should be larger, and this reading should definitely be larger than 1 meter. And this is actually the impact of the sag. And we also need to do the correction about the sag. And there, fortunately, we have the function to calculate the correction from the sag. So what you will observe is like this function. It's even though it's quite complicated, but still there's a way for us to do it. So the correction for sag, CS equal to little w square times L cube divided by 24 times P square. And it also equals to W square times L divided by 24 P square. So in this equation, the little w is the weight of the tape. So it's the it will be the unit weight of the tape. So this is something we have to specify. It measures as the unit of this one is pound per feet or kilogram per meter. So it's the unit weight of the tape, and the capital W is the total weight of the tape between the support, which would be the for this case, this would be the total weight of the tape in this region, from point A to point B. If it's measured as 1.01 meters, then that will be the weight of 1.01 meter segment. And the L, capital L, is the measured length, which is the is how long you measured for each measurement. And the P is the applied tension, which is the force or the tension you actually apply to conduct the measurement. That's also the reason it's very important for us to always recording the tension, because the tension is not only related to the correction of the tension, but also it's related to the correction for sag. So the if we go to check the relationship between the tension and the correction for the sag, you can see that by increasing the value of P, which means that you increase the tension applied to the tape, then the value of the correction for sag will reduce. And this figure actually shows the relationship between the correction of the sag with respect to the tension for three different tapes. For the very heavy tape, the medium weight tape, and the medium weight tape with a length of 25 feet. Generally, if we are provided with the if we are given the weight of the tape and the length of the tape, in that sense, the correction of the sag is a function of P, of the tension applied, and this function is has two features. First, as a convex function, as what you can see in this graph, if the correction the correction reduced significantly when the tension is small. At a smaller region, you increase the tension, you will have significant reductions about the correction for the sag. But when the tension is forced at a large region, then the correction reduction will be smaller when you increase the tension. And we can see the convex relationship and decreasing relationship. With larger, basically with larger tension, the correction for sag would be smaller. And another thing that we want to, I think I don't have enough time for that. So we will have 7 minutes left, and I will now assign you to the quiz, so that I forgot the time a little bit. So for now, you can go to the Avenue to Learn. If we go to Avenue to Learn, under the assessment, I'm just going to show you. So you go to Avenue to Learn, go to assessment. And in the quiz section, you can find out the quiz. And I haven't made it visible for you now. And now it's visible. So you can go there and working on the quiz. There will be 2 questions there. One is about the calculation of the zenith angle and the vertical angle. The other one is about the calculation of the horizontal distance. So you can work on these 2 questions. And I think we don't have enough time today, but I will show you the solution in the next lecture. So you will have 5 minutes to work on the quiz, and the quiz will be disabled after 2:20. So so you can start working now. Let me know if you have any questions. So can you see the quiz now? Okay, that's good. That's good. You can work on the quiz and let me know if there's any question. It's just try your best to work to get the right answer, even though it's not a graded based on better get the right answer. But I hope you can have some practice about how to what's the relationship between the zenith angle and vertical angle, and how to use the formula we defined in the previous lecture to calculate the horizontal distance. I will probably stop recording the video for now.